Hello and welcome to this episode of T-Tech. So this is going to be a series where we're going to talk about the Cisco IOS devices. So pretty much most devices Cisco. We're going to focus on routers from Cisco and switches. But the main thing I want you to take away from it is the configuration of the devices and some of the concepts behind the technology we're going to be using. So the first thing, I don't care if it's a Cisco device or not, you need to understand that, these are physical devices, even though we now have virtual devices coming out that are in heavy use in situations where the cloud's involved. Physical devices are still needed. So, this is my Cisco router here. And the main things we're going to be working with a lot of the time with these devices is the console port. Now, I don't know if you hear the fan in the background, but that's the router running. And I'm actually plugged into the console port of it. So this is that port. You plug into there with a roll cable. You have an auxiliary port. And you have a WIC module. That's what the W0 stands for. It's a slot that a WIC card will fit into. And this particular one is a T1 card. But what you want to know is these devices can have expanded functionality. When you want something extra that the device doesn't ship with, you add a WIC card to that device, and it gives it more functionality than what it had when it was purchased. So these cards, they just pull right out of there, and that's what one looks like. It has the appropriate connectors for, this specific brand of device. And, it slides out of there, you unscrew the screws, and it goes out there. Make sure you power the device off first before you deal with anything with a WIC card. It's not safe to unplug them when it's on because they're not hot pluggable. It isn't like something like a RAID array of disks where that's designed to pull the disk out safely and replace it. It's not the same thing with these. So that's our main devices, the physical ports on our devices. The last thing to keep in mind is ports like these. These are our network connection ports. And in this particular case, these are 10/100. That refers to the speed. So these are 10 and 100 megabit per second connections. And the Ethernet refers to the data link layer. So remember, that's layer 2. And that's what these run. The last number in the name there is the number of the port. The first number is the slot, so the slot it's in, because on bigger devices you can have many different slots. And the second number there after the slash is the port on that slot. I have a switch, for instance, that has a bus number and then a card number and then a slot and then a port on that card. So it can get more complex, but all you need to know is that's the numbered ports. And that's all you need to know there. So anyway, with that though, we're gonna use PuTTY in the next step here, and we're gonna go into the real router and take a peek around in it, because the rest of this is gonna be in Packet Tracer. The reason being is it's easier to show you more complex configurations that we're gonna get into later on. So I will see you in the next section. Alright, so now in Packet Tracer, to connect to pretty much any vendor's network equipment, whether it's a router, switch, anything like that, if it has a console cable and it uses serial, all you have to do is check this box here that says serial, and what you put here for the serial line depends on your OS and how it detected the device. Now, in my case, I went into Device Manager under the Ports heading, the section in there, and mine is COM6. So we're going to go here and change this to be COM6 instead of COM1. Now, the next thing is speed, and this is the baud rate of the device. Now, by default, the device I'm using, the Cisco router, has a 9600 bits per second speed. And if that is changed for any reason, it'll be different, and you have to make sure you set that correctly. Otherwise, you're not going to be able to see usable output on your console. And other vendors do have different speeds. So, like for instance, if you're on a server that's running Linux, a lot of the time they use 115200. That's built into Linux, but it just depends. And you will find that a lot of these devices have Linux or are running some Unix-based OS in them. So, you can go pretty far with knowing that knowledge about the baud rate there. So anyway, from there, though, you just hit open, and then it should open for you. And if you have the settings correct, you will see the device's console output there. Alright, so now we're in the router here, and we're in user mode, so we have very limited privileges. So I can't do like show run. The full command there is show running -config. It doesn't understand that command because I don't have rights to run that. To run that command, I got to do enable to get to privileged exec mode. Privileged exec mode is basically having root on the device, although that term doesn't exist in iOS from Cisco, so it's similar but not the same. So here, if we do show run, we can see the basic configuration and show. You can also do full commands like that, or you can abbreviate them like this. Okay, and that's basically the idea of a real device. But most of what you're going to see and configure is going to be pretty much spot on in Packet Tracer versus the real device. So from there, though, I just wanted to show you a real device to see what you'd be dealing with there. It's pretty much the same, other than having to physically plug in a console cable. So now we're going to move into the Packet Tracer Labs, and I'm going to basically do all the stuff I would do on a normal device, but it's going to be much easier for you to actually visualize the concept. So I will see you inside our first lab, and we're just going to discuss, we're going to do the initial configuration of a Cisco device. So I will see you in the lab. Alright, in this lab here, we're going to set a host name, create a user, set the enable mode password, and secure the console, aux, and V2 lines. So finally, we're going to tell the device to use these settings that we set. So in Packet Tracer, just go ahead. Once you drag the device out, just click it. Alright, there we go. Well, it's a little bit better there. Okay. So, once I hit return, you see we're in user mode. And pretty much looks like this same device as the real router. And we're just going to say enable here to get to root. We're going to do configure terminal. And that gets us to basically where we enter all the commands here for the device. And these take effect immediately. So the first thing we'll do is do host name. I'm going to name it TTech. You see how it changed that host name immediately, and that's what happens. After that, we're going to make a user, so username, admin, secret, and Cisco 1. Now, you can use password here, like this, but that command does not perform a one-way hash on the plain text. This value, the Cisco 1, In order to make that happen, you have to use service password encryption if you use the password argument. Usually, it's best to use secret unless your iOS is older or something for backwards compatibility, but we're going to use secret here and hit enter. Now we want to protect the enable mode. So we want to say enable secret Cisco. You want to have a separate password. You can use password, but again, you want to use secret most times. Now we're also going to set a banner. So banner, and then we're going to pick a character. And now we're going to type our message and then end with that same character. Now, you also want to type the type of banner this is. And this is a message of the day banner. So we want to type that, hit enter. So now we want to secure the lines that we talked about. We want to say line console 0, and we need to use the username we made up above. So we need to say login space local, and this tells it the only time it will allow someone to connect to this console port is if they put in a username in its database, in VRAM. So this device locally. And in this case, it's admin and Cisco 1. So login local means you have to put that in there to authenticate to the console port. We're also going to say logging synchronous. This helps so commands don't get cut in half by logging messages. Now we're going to say line aux 0. This is the auxiliary line. And we're going to say login local for the same reason and logging synchronous for the same reason. We're also going to say line VTY 0 and then question mark. And then we're going to say 15. Now, every device has a different amount of VTY lines. It depends on the amount of RAM, also known as DRAM, in the device. So we have 15 here. We're going to say login local and logging synchronous. Now, the VTY lines are used when you connect to the management plane of the device. And that is over the network, either with Telnet or SSH. All right? So that's what the lines here keep track of. So we're going to exit. Now, a few other things you might do to a device as well. You may set clock, time zone, and then you can choose your time zone. As well as network time protocol, you may set the server, as you can see here. There, you'd put the IP address of an NTP server. Since this is packet tracer and not a live network, it's harder to show you that. You can do that in packet tracer. You can use the server device and pretend to set one up. Finally, we're going to go ahead and hit end and see this message without logging synchronous would have been cut in half of that command. So we're going to say copy running -config to startup -config. So the startup config takes effect. It's the instructions the device is going to run every time it starts up. The running config is everything the device is doing at the moment. So this also includes if maybe you messed up a configuration, say an IP address on an interface, and you lost connectivity, at least over the interface. But if you have console, you can reload the device or have someone power it off. And if you didn't save it before that, it comes up with the old startup config, and that would save you from problems there. So do be careful with the difference and the changes you're making before you do this command, to actually copy it into the startup config, because if something's wrong, it's going to keep coming up with that. And you're going to have to, bypass the configuration by changing the configuration register value. But we're okay with this. That file name's all right, so we're going to hit OK on that. I do want you to know you can like after you back that up, or maybe the running config as well, you can abbreviate these like copy start and copy them to a TFTP server as well, and then you put the IP address of the server. We don't want to do that right now though. But if we show start, that shows you the config there. So that's how we set the basic device settings. So next we're going to set up an IP address on the interfaces. Oh, I actually want to show you one more thing. If we exit out, you see we have that here. And we have our banner. And now we have to type that right password. And enable. And we got to type the right password. So now it's all protected for us. Alright, now we're going to set the IP address. So we're going to go ahead and log in with what we just set. And say Cisco 1 enable and Cisco. Now we're going to do show IP interface brief. What I'm going to do is set an IP address on fast Ethernet 0/0. Okay, so we're going to configure terminal, and these are the abbreviations I was speaking about. Now we're going to say interface, all right, fast Ethernet 0/0. And then to set an IP address, we're going to say IP space address. And for the lab, I'm going to set 192.168.1.1. And after this, you have to set a subnet mask. This tells you how much of that address is the network that can't change, essentially, and how much of it is the host to actually assign on this network. So we're going to do 255, 255, 255, 0. And we'll hit enter there. Now, there's something important. Just because we set the address, there's two things we got to keep track of. If we do show run right now, the IP address is on there, but you'll see something in that block. It says shut down. On an iOS router, an interface is off by default. It can't send or receive traffic. So we actually have to do two things. We have to go in there and go into that interface and say no shutdown. And you see the interface state is changed up. And we also have to go into here and do copy run start. You remember why? Because otherwise, if we reload right now, before doing that command above, it wouldn't save the IP address on that interface. So now that we do show IP interface brief, we have that the interface has its IP. And it's all up and running. Now the reason protocol is down is because there's nothing plugged into the other end of it. But we'll fix that a little bit later. So that's how we set an address. And again, don't forget, copy run start to save that configuration. Alright, so now we're going to configure DHCP. So this is Dynamic Host Configuration Protocol, and this will give the clients on the LAN the addressing information they need automatically. Now, there's actually two ways to do this. And the way I'm going to show you is actually with a DHCP server that is built into the iOS software. There's another way, and what we would do here, just to give you an idea, is we would bring out a server and attach that to our existing network into this switch. And this server would run the DHCP server software instead of our router. In a bigger network, that is what you would do. Both ways achieve the same goal. It's just that one of them is a little bit more scalable than having one router. Okay? So we're going to go ahead and remove that real quick. There we go. Now, we're going to go into the router. And let's bring that up there a little. All right. Now, I'm just focusing on this config, and you would pair this with all of the basic commands we've already talked about. What I want to do is set an IP address here on F00, so that's the one connected into the switch. We're going to set the IP of 192.168.1.1, and this is a /24 mask. And then remember, you want to bring that interface up. You have to do that. Now, for DHCP, when we create our pool, also known as a scope, the DHCP server will start to listen for DHCP broadcasts from the network, and it will start to respond. And any IP address within the subnet that it's going to lease is able to be assigned, including the IP address of our fast Ethernet 0/0 interface. So before we set up our DHCP server, we want to stop it from being able to hand out that specific address. And how we do this is with IP DHCP excluded dash address, and we're going to put in the address we don't want to hand out. All right, and if we have a server, which we'll see coming up next, we'll put other addresses in there as well. Now, to do the actual server, we're going to do IP DHCP pool, and then we'll call this one LAN. It doesn't have to be uppercase. That is just for the administrator. So now we're in DHCP config mode. All right, we were in global configuration mode with configure terminal. Now we're in DHCP-config mode. The first thing we want to do is network, and then we want to put in the network ID, and you get that by taking the mask and that IP address and then finding the beginning of the subnet. Those two values, once you study more about subnetting, they help you find the beginning and end, as well as the available addresses in between the beginning and end. So that's our network ID. That's the start. So we're going to put 255, 255, 255, 0, and we want to enter that. So after that, we need a few important other IP addresses to put in here. We need default-router, and this is the default gateway that clients are going to send their packets to. And then this should be the fast Ethernet 00 interface. All right. And we also want to put in a DNS server so they can resolve domain names. So we're going to put in DNS-server. And then we're going to put in 192.168.1.254. Now, you can also put in another public one like 8.8.8.8, especially on real equipment. But we put that one in because we're going to set one up next, and that's going to point to it. But essentially, we need the network, we need a default router, and we need a DNS server. So we're going to go out of back to privileged exec mode, and then we're going to copy run start. You can also write, but the write memory command is a little bit depreciated compared to copy run start. And we can verify it by doing a show run. You can look, you can see this means the router is running that DHCP server configuration right now because it is in the running config, and the running config is in RAM. Now, if we do show start, you can verify that the router is going to come up and configure itself to be a DHCP server with that configuration, and it is. So now we can verify our pool with show IP DHCP pool, and if you have more than one pool, you can specify it, especially on a bigger network. You can see all the information about it here. That's very important to check on from time to time. So now, though, we're going to, let's exit this, our router here, and let's bring up one of our PCs connected into the switch. So if we go to desktop, command prompt, do ipconfig on there. It doesn't have an IP yet, but if we do ipconfig/renew, it's going to send a discover message. This server is then going to hear to that, then send an offer, then we're going to request it, and it will acknowledge that we requested this specific configuration. And that's what's happened here. We now have the IP address 192.168.1.2 for a specific amount of time, and that's determined by the DHCP server. You can configure that with the lease parameter as well when you're in that mode. The net mask we put in there, the default gateway, and the DNS server on a real device. This doesn't have to be Cisco. This could be any vendor that runs a DHCP server. You can put in secondary DNS servers. Just in Packet Tracer you can't, so I can't really show you that, but it's basically a backup if that fails. So with that, though, we can ping our gateway now, because now we understand the subnet we're on and everything. So if we go back here, and then let's go to our other PC just to verify. Because another thing to make sure of, just because one PC can get an IP address doesn't necessarily mean everything is working on all of the PCs in the network. This is the case this time, though. So we're all good on that. So let's go to the router one more time. And we're going to do show IP DHCP binding. And this tells us our leases and our lease expiration, our type, and the MAC address. So the specific network card in that computer is logically assigned that IP address to the left there. And then that follows it through the network. The MAC address will always stay the same unless it's being spoofed, but the IP address is assigned, so they're temporarily assigned together. But that can change. And in a bigger network, you may be in another floor or another building, and you might use a different DHCP server, or at least a different scope. And that will make more sense later on. But what we're going to do is do show IP DHCP pool, and then look at the pool options here. You can see we have 254 addresses. 2 of them are leased, and then 1 is excluded. Remember, that's our gateway, the Fast Ethernet 00. But why this is important is if you run out of available addresses to lease, you get in a situation called DHCP exhaustion, and that's when you're running out of available leases. This can actually be done maliciously as well in a network-based attack to, starve out the DHCP servers on the network and run a rogue one and give fake network information. But that's the security side of networking. It's really deep. But this is a basic DHCP server, and you can do it either on a dedicated machine that runs DHCP software, a server itself, or you can do it on the Cisco device itself. So with that, we're going to move on to the next one, and we're going to set up a DNS server in our network. All right, so now we're going to configure the DNS server in our network. So the difference with this is, being internal, you can do things like have resources that are local be addressed with DNS. And you can also speed up resolution of external resources. So you don't have to ask a DNS server out on the internet about a domain name. What can happen is your server can additionally cache the domain name. So this is why it's important to know about this. So let's bring that server back out. We still have the DHCP server set up here. And what we're going to do is go in there first before we roll this out. And we're going to say IP DHCP excluded address 192.168.1.254. The reason is that is our server's IP address. And remember, just like the default gateway, we don't want to lease out the static IP address of our server. So we're going to configure its IP address here, and under the IP configuration, just like that. And you want to give it a gateway, especially if it's a network with multiple subnets, and you want this server to be available from any of those with something a little bit more advanced called DHCP relaying, where one subnet, even though it's not connected directly to this server itself, can still access the DNS server. But for this server's own DNS server, we'll just put 8.8.8.8. The reason is it's not going to know about everything. It only knows about the domain and what's called the zone that it's responsible for, and that everything else would be answered by the server here that gets its answers from additional DNS servers called the root servers. So let's go ahead, now that we've set the IP, and we want to hook this server in to our switch. And I'll just put it on port 23, it doesn't really matter. And you remember, a managed switch runs spanning tree protocol, and that prevents loops. So we want to let that finish running before we set this up. And it may delay certain things in your network and things of that nature. So let's double check our config. All right, we got the right IP for our DNS server, by the way. And let's go into the DNS server under services. Now, in reality, this would be something like bind or NSD. You can also use unbound for this. They all basically can serve the same purpose. It's just that some software doesn't do things like zone transfers and other things like that. So we're going to put in basic domains that we're all familiar with, google.com, and we'll just put that as 1111. This is an A record, and what that means is this mapping is for an IPv4 address. I don't believe Packet Tracer lets you use quad A records or anything else. That's okay, though. It's good enough for what I'm trying to explain. So we'll also put Yahoo in there. And 2222. This is an A record. Now, there's other records like MX records. Those are for, excuse me, resources like mail servers for a domain. If you want to email a domain, you query a DNS server for that domain's MX record as well, not just the IP address with the A record query. So that would allow you to send mail to the mail server for that domain. But these were just dealing with two IPv4 addresses and two different domain names. And let's also do this. Let's put in something called a web server here and pretend that let's pretend that it's on our network somewhere. 253. There we go. So this is split DNS, where this is our local. What would happen is this would be different on the public internet, and then this one would work if you were inside the network. So that's called split DNS. So there's a lot to it, but I'm just trying to show you the basics of what goes on with it. So we're going to go back to the PC. And we're going to go ahead and release and renew. All right. Now, if we do ns lookup, and if we query that domain name server for google.com, we're going to get 1111 because we just put that in the zone file of our DNS server. In reality, if it didn't know that, you would place a forward zone in it and tell it what servers on the internet, so upstream DNS servers, which ones it should use to resolve the name if it doesn't know. So it would do the same thing your computer is doing right here, but it would just ask a DNS server that is on the internet somewhere instead of in the local network, like this computer's doing. So if we look at yahoo.com, because we have a record there, it's 2222. And if we look at that web server, we're going to get a local address. And what we would do is web server, which it would be a normal domain name, obviously. But if someone was coming in and then this was the WAN here, they would get a different IP address. They would get the public address of this interface. And there's other configurations that can be done with that as well, but that's outside of the scope of this discussion. So that is how we do this, though, with DNS and why you have it in the network like this. Now, you can also use the DNS server in iOS, but unfortunately, that only works on a real device with a real iOS image. The command is IP DNS server, and then you would put in IP host, and then you'd put in records for the IP addresses, essentially. So you could put IP host like 192.168.1.253, and then you can tell, you could put in like google.com, and then the IP address, like how we just said, 1111. And then that would put that in there. And then if you put in IP DNS server, then your clients could query the router directly instead of a dedicated machine on the network. And then you'd also can put in IP name server to tell it, like for instance 4222, etc. For the other servers, it can query if it doesn't have an answer for that. But they don't have that implemented in Packet Tracer, which is fine. But if you're on a real device or if you have lab equipment, you'll be able to also do DNS on the router itself. And it can do that in real life, just not in Packet Tracer. But with that, though, that is how you configure a DNS server. All right, now we're going to talk about VLANs. So these are virtual local area networks. And the reason we want to use them is because it helps us secure and consolidate the networks. So essentially, we can get away with using less gear, so I only need one router here, one switch, and a cable for each PC. It doesn't matter physically where this PC is or anything of that nature. As long as it's in the VLAN it's supposed to be in, it's part of that network, regardless of where it's located. So we're going to first, essentially what we're going to do by the end of this is have VLAN 10, and VLAN 10 will be right here. And we're going to have VLAN 20. So these will map with these subnets. So there's two parts to this configuration, at least in this version of how I'm doing it. And this is called router on a stick. And what that essentially means is that you have one router and it's doing inter-VLAN routing. Now, there's also another way to do it with a multi-layer switch, which is a switch that does routing as well, but we're only going to focus on this for now. So I'm going to go into the router, And what I want to do here is look at our interfaces real quick. So do show IP interface brief. And I'm going to use Fast Ethernet 00 as my parent interface essentially. So I'm going to say no shutdown. That's all I need to do on that interface. Now I'm going to say interface F00 dot, and then after the dot, this is the sub interface part. We're going to say 10. Now this is for VLAN 10. So when I hit enter, it creates a new sub interface. Now we can do most of the commands we can do on a real interface on this type of interface as well. What we're going to do is set the IP address, and this is going to be 192.168.10.1 with a /24. Oops, I'm sorry. You do got to pay attention to the order. You have to first do encapsulation.1q, and then we have to say the tag ID. So this is 10. And then we're going to say IP address 192.168.10.1 with that subnet mask, just like a real interface. You don't have to say no shutdown, but it's good practice because you get in the habit of it when you end up with an interface that it's important to do on. So we're also going to say IP NAT inside at this point because this is part of our inside domain of NAT. And now we're going to say interface F00.20, and then we're going to say encapsulation.1q20, set the IP address 20.1, all right, no shutdown, and then IP NAT inside. So now if we look at our interfaces, we now have the main Fast Ethernet 00. You can assign an IP address to the interface and use it as a management network, not being routed anywhere else, or just use a dedicated port for that. But it should be up and up. That should be its status, and the same thing with the VLAN interfaces for the two networks. And also make sure by now that they are in the right the inside interfaces portion. All right. So now we're going to go into we might as well go into our external interface and just set basically a mock IP on there for us, just to show you the complete configuration. And now we're just going to set up DHCP servers for V20. So this will be for VLAN 20. And you can still do the excluded addresses and everything, but your default router will be that sub interface's address. And the DNS server, again, it can be multiple things. If you want to use a relay, you could say that it is on 10.254 on VLAN 10, and then use DHCP relay to access that. But we're just going to say right now that it's going to be on the same VLAN 10.254. All right, and we're going to say the same thing for the second pool, the next VLAN, VLAN 10. And then the same thing for the scope and the default router. Should be 10.1. And then DNS. Again, we're pretending it's in the same network. It doesn't have to be. Let's save that configuration. So now we should have two DHCP pools this time, and we do. And we should also have our interfaces set up in their appropriate VLANs and everything. And as well, we should have the NAT set up correctly, and we do. So now we're going to exit out of there, and then we're going to go into the switch, because the tags that are put on there are only when it's sent away from the router toward the LAN, and so out the parent interface essentially. So Fast Ethernet 00. But the switch also has to do the tagging when it's sending it up to that interface, because the clients themselves don't know about 802.1q, which is what makes VLANs operate. It's the trunking protocol that adds the tags on there. So in order to do this, we just need to create two VLANs. We're going to say VLAN 10, and that's going to be Office, and then we're going to say VLAN 20, and that's going to be like, we're just going to say a DMZ for now. So from that, we need to go into the right interfaces. So we're going to say F01, and that is what the PC in VLAN 10 is connected to. So we're going to say switch port access. It needs to be an access port. Whoops. Switch port mode access. Switch port access VLAN 10. And then we're going to go into the second port in this case. And switch port mode access. And then you want to put, with the access command, you want to put it in the correct VLAN. So because they're now in different VLANs, logically, they will not be able to communicate. So for our, in this lab now, they are separated. They're not physically separated, but they're logically separated. They're still part of the same switch, but they're acting like they're two different switches now. So this is breaking up the broadcast domain on the switch into two broadcast domains now. So we're going to go ahead and go into fast Ethernet 0/24 and do switch port mode trunk. And the reason is because this is going to carry the VLANs up to the router. And essentially, you can say switch port trunk allowed VLAN, and then we can add 10 and 20 only, and that essentially means it's only going to carry those VLANs, because otherwise you can have security issues happen and things like that. But what we should have when we're done is we have our default VLAN in those ports, and then we have our Office and DMZ. Now another thing you should do is shut down the ports that are in VLAN 1. Alright, because you should move those to an unused VLAN and shut them down for security, because you don't want anyone using those ports in your network. So what we're going to do now is save this configuration. And we can do show interface trunk to verify, just like we did show VLAN. And that's what you want to see. Port FA 0/24, it's on, the encapsulation is 802.1q. It's trunking, the native VLAN is 1, and the native VLAN is the one that will not have a tag put on it. And that's, you can change it for security purposes, or you can leave it alone. So you also see that we only have ports 1, 10, and 20 allowed, and that's fine. That's what we did with the allowed VLAN command. Now we're going to exit. And with everything set up, we should be able to get an IP on this side of for this device from the DHCP server for VLAN 10, like we just did. And let's try to ping that device. And 1 second there. Alright, that's weird. Oh, it's not weird at all. I pinged the wrong IP. 10.1. My apologies. So we can ping there, and that works with the VLANs. And then if we look here, and again, this can be physically anywhere as long as it's in that VLAN. So 20.1 and good. Now, because there is no access control lists or anything, we can ping across to the other devices. So we can, this is inter-VLAN routing. It's coming up, going to the router, going back down to the switch, and then the switch is only sending it out the ports that are part of the VLAN. That's why getting the correct tag associated with the correct ports is very important. Because if it's associated with the wrong port for any reason, you can have a problem where frames can go to the wrong devices and have access where they shouldn't. So with that though, that is how we do VLANs. And again, without VLANs, I'm going to quick show you, we would need essentially let me find a switch here. In the 2960s are layer 3 multi-layer switches, but just to show you the difference, we would actually have to have a lot more ports on the router to do this. We'd have to have that port. And this one plugged in, as well as additional ports to the clients. And you can see how that can be quite more costly, because now we have 4 cables where before we had 3. Now we have 2 switches where we had 1. So that's the concept of VLANs and why they're important. Alright, so now we're going to talk about NAT, or Network Address Translation. And the type of NAT we're going to be talking about is specifically SNAT, and what I mean by that in this context is source NAT. So what we're going to do is basically with network address translation, we have groups of IP addresses that can be reused in every network in the world. They aren't unique, they're reused, but because of network address translation and a pool of public IP addresses here, all of the computers in this network here have a private called an RFC 1918 address. So that's a request for comment. And this group of private addresses, even though it's in every network in the world that uses IPv4, the NAT function, the source NAT, changes that address to be a public IP address. So that public IP address is part of what is routed basically by your ISP. All right, and the ISPs even use private addresses for management of devices and things like that. And that's why you can't route a private IP address into an ISP from your network, from your own LAN. It's going to be dropped. So how this looks is our ISP up here actually has essentially access lists. Obviously it's not like this completely because this is packet tracer, but this is the idea. We have 2 access lists that blocks it on the interface to this customer and the interface to this customer. And we're denying the 10.0.0/8 network. We're denying the 172.16.0.0/12 network and the 192.168.0.0/16 network. Those are the 3 RFC 1918 network blocks. We don't want those to enter our customer-facing interfaces. The only thing that should be entering those interfaces are the public addresses that our customers should properly be using NAT. So that's what the ISP is expecting. And that's why we set up NAT as network administrators. And, even home users or curious users, you can do this on other devices. If you just do a little bit of Googling, you'll find a lot of interesting things. So everything else, though, is permitted C. So that's why we need to use NAT. Now, what I'm going to do first, because I've already set up DHCP here, so we're going to go to this PC. And let us see here. So I can already ping my gateway. And also that 1.1.1.2 end there, that IP address, I can ping that because it's on my local router, but I cannot ping 1111. It's going to time out. Same thing if I try to route over to the other customer, it's not going to make it. Now, why is it timing out, you think? Well, if you answer because when it's being sent out to the ISP here, maybe it's still one of those private addresses, you're right. Let's go up here and rerun that command. And you'll see we have two matches for the 192.168.00/16. And that's because the NAT in the routers isn't enabled. So we have to go through some steps to make that happen. Now, first thing we got to do with the NAT, identify our inside interface and outside interface. So my inside is fast Ethernet 00, and my outside is serial 000. On a real ISR router, these can be Ethernet interfaces going into a cable modem, a fiber modem, whatever. It doesn't have to be a T1 interface or a serial interface. So we're going to go to global config, and let's go to F00 and set IPNAT inside. All right. And now we're going to go to serial 000 and double check. Yep. And IPNAT outside. Now that sets the NAT domains basically. The outside interface is here, the inside is here, and if you have a bigger network, you'll have many interfaces on your inside interfaces, like sub-interfaces and things like that for VLANs. But from there, we need to make an access list. So IP access list, standard, we just need to focus on the source IP address in the packet. We're going to have this be a named list, so we're going to say NAT, and we're going to say permit 192.168.10.0.0.255. And that is our LAN. We don't want to permit anything else. But this says the traffic that matches this access control entry is going to be it's going to be NATed. It's going to have its source address changed. So we're going to exit there, and then we're going to put this all together with IPNAT inside source. This is where it's getting this NAT rule from, essentially. And it's going to be a list. It's going to be called NAT because that's our access list. And the interface that is going to be the public address or the global address in the terms of iOS is going to be S000. Now, one more keyword is going to be overload. What this does is it maps every unique outgoing connection through this router to a different source port. So it also rewrites the port at layer 4, not just the source IP address at layer 3. All right, this is important because if we don't put this, the first client on the LAN to use this router will be able to use all 65,535 ports, and no other devices will be able to get out to the internet at the same time. So that's a very bad thing, obviously, in your network. You don't want that. So we're going to put that in there. Let's save that configuration. And essentially, you do the same thing on the other side. And let's quick go ahead here and do the same kind of idea, like this here, and IPNAT inside source list NAT interface S001 overload. All right, and now if we go here back to this guy, we should be able to ping the 1111, and we can also ping the 2222 because the source address is changed. So that is how source NAT works. All right, so now we're going to talk about DNAT. And this is, in this context, destination NAT. And what we're trying to do with this version of NAT is basically the reverse of what we did with source NAT. Instead of taking a private RFC 1918 address and changing it to be a public address, we're taking a public address that has no existing connection in our network at all. And it's going to come in, and in order for it to make a connection to a service inside of our network, we need to change the destination from the one public address that our router has to whatever the private address is behind it. So in my case, we have a public client up here on the 2220/24, and in this case, that is the source IP address he's coming in from. Now, he is in reality sitting behind a router running NAT, so he's also in an RFC 1918 address space. But because the source is public, that's what I'm focusing on here. The server is on the private side, and that server here has 192.168.1.254, and we're also running a web server, and it's using HTTP. So what we're using is port 80 in this case. And what we want to do is open up our client, go to the web browser, and then let's try to go to the public IP of our router, 221. And remember, this would be linked with a domain DNS server's A record. All right, this is how it fits together. So if we try to go right now, the server is going to reset the connection because that is saying on port 80 there's nothing there that's going to take your connection. Sorry. So there is two ways to do it. You can do it that way, or if you want to have more security, you can block that response. So that's another thing to research. It's a good thing to do. Now, what do we do to make that packet going to port 80 go through the router and get to the private side? Well, let's see. What we have already configured is our SNAT. So we've set our inside and our outside interfaces, and everything else is set up okay. Now, if we do show IPNAT translations, there is no translations, either outbound, dynamic with the source NAT, or inbound. So what we want to do is go into global config, and then we want to run IPNAT inside source static this time because we're typing what we want in here. And we're going to say TCP because that is the layer 4 transport protocol HTTP uses. And then we're going to say the inside local address, so 192.168.1.254. And then the port on that inside address is 80. Now, if you're using a server where you don't want to run it as root and you want to run it on a non-standard port, on the inside, you'd say something like 9000 or, 8081 or anything like that. But for now, we're going to say 80. And the global address is 2221. That is the address that is representing this device on in the private address space. The 2221 is the global address. It's representing this device on the inside that has the local address. And the port on the outside that's going to represent this mapping is 80. Again, those two ports can be different. You would use the standard port that your clients expect on the outside, and then you can use a non-standard one on the inside if you need to. So we're going to go ahead and hit enter on that. And now if we save that configuration and then do show IPNAT translations, we have a static one in there. The inside global address is 2221 on port 80. The inside local is 192.168.1.254. That's also on port 80. And outside local and outside global are not for something like this. It's for something different. But now that we've saved it and everything, and even if you don't, that goes in the running config immediately. We're going to go ahead and exit out of here. Let's go to our client. Remember, we weren't able to get through before. And now if we go 2221, now we can get through to the server in the private address space. So, now if we open up the router real quick, we can see with a show IP NAT translations that we have incoming port 80 connections, and the outside local is the outside address that is connecting into the inside local address. And so this means that 2222 is using that as a source address, and the source port is TCP 1026. And there's no NAT being performed on this address before it hits the server, so those are going to match on the outside as well. But the inside local is different than the inside global because this address as a destination and that port is being changed. The layer 3 address is changed to this 192.168.1.254. This case, the port is the same, but you can change the port number as well at layer 4 for the reasons we spoke about before. But with that, though, that is how destination NAT works. And this is also just known as a port forward in normal SOHO gear, but it's the same concept, and that's why you do it. Now, I want to talk about one more thing that you may find interesting. In some situations, if we move this stuff down a little bit, we can move this server. Well, let's get another server to show you. It'll be a little less confusing with that there. We can move the server into this kind of zone. So it's still in the network of this network, but it's in the public part of it. So what we would do is get a public block of IPs from our service provider, and we would assign one of those public IPs. For instance, if we go into the server and go here to the IP config, let's say we got 3333, and I don't want to use any real public IPs, obviously, but let's say we got a slash. Let's say for some reason we got a slash 24. Very unlikely you're going to get that many IPs. You're going to pay quite a bit for that. But let's say we got that block of addresses. Well, actually, yeah, slash 29. So with that, we'd be able to, we don't need a default gateway in that case because we're sending right back out. Well, the default gateway would actually be at the ISP in this case. So essentially then you wouldn't need NAT is what I'm saying. So they would just connect right in. And that is another way to do it. That's how the cloud is set up a lot of times. Your server is just public on the internet, and then, you know, how we said the providers use private addresses. It's the same thing. They use privates to manage their equipment and things like that. But with that, though, that is destination NAT. So I will see you in the next one. Alright, so now we're going to talk about static routing. Now, routing is just the process a router performs in order to send the packet closer to where it needs to go. Because remember, routers connect IP networks together, and they can have many different routes to get to the same destination. So essentially, though, the routing part is the instruction of how to get to that destination. And essentially it says, if your packet has a destination of, let's say, the 10.0012/30 network, we're going to send you out interface B. if it has the destination 10.0.0.0/30, we're going to send you out interface A instead. So that's the idea. But before we can set up any routing, we need to assign the interfaces on these devices those IP addresses. So we're going to first assign, we're on the top router, and the Fast Ethernet 00 is the interface on the 10.0.0.0/30 network. So we're going to assign that 10.0.0.2. And remember, it's a /30 mask. And you have to bring that interface up. And we're also going to go from there into the serial 000 interface. And this interface is on the, the 10.0.0.4. So we got 10.0.0.6 on this segment. And then that's going to be a /30. And you want to bring that up. So that is all the interfaces on that machine. We're going to save that config. We're also going to say this is R1 and save that config. Now we're going to head over to the middle one. All right, we have F00 on this interface. And he was part of that same 000 network, except this one is going to be .1. But they fall in the same subnet. So we're going to bring those up. Now let's do ping 10.0.0.2. We want to make sure we have connectivity. Okay, good. Let's also go to the second interface and assign the 10.0.0.9 address, just like that. And don't forget to set the host name. All right. Then we'll go across to the next router over there and do hostname R3 and then set. These on this one are going to be serial interfaces. So we're going to set those. But you set the IP the same way. So this is going to be 10.0.0.5 with the /30. And then we're going to go over to S001 and set 10.0.0.13. Whoops. All right, there we go. So we'll do ping, and we want to test connectivity to the 10.0.0.6 interface on that router. Okay. Now we got one more router to configure here at the bottom. It's going to be R4, and we're going to go into F01 and set the IP on this router, 10.0.0.10. And then no shutdown. And then S001 and set that IP address there. This one was 14. And no shutdown on that. So the reason we went through all that is obviously to get IP addresses on the interface. But the interesting thing, anytime you're dealing with a router, you have directly connected networks and you have indirectly connected networks. So if we do a show IP route, we see two directly connected networks. Remember, we put this IP on the Fast Ethernet 00, and with that mask, that tells us that it falls in the 10.0.0.0 network. All right? So that broadcast domain and IP subnet is part of Fast Ethernet 00. Rather, that interface is part of that subnet, that broadcast domain. The serial 000 is part of the 10.0.0.4 network. It's directly connected, And that means you can get to it right on this router. You don't need to route to it. The router already has it in its routing table. That's why we can ping anything connected to this that is connected to this subnet, because we understand what that subnet is and what interface it should go out of. But what we don't understand is when we want to ping the 10.00.14, let's say. If we try to ping that, we're going to get timeouts. The reason is it doesn't know how to get to that network. And if we look at our routing table, and if we try to look at the subnet that is on the network ID, it says subnet isn't in table. And that is where the routing comes in. So what do we do here? Well, it's fairly straightforward. At least, in practice, these routers could be in very different, locations physically. So essentially, it could take quite a bit of cooperation with this. But essentially, we're going to go into our router here, and we will say we can get to the 14 network out of that serial interface. So we're going to say IP route 10.00.12. That's the network. And the mask is a wildcard mask, so not a wildcard mask. So we're going to have that be a /30 mask like it was. But we're going to use the next hop address. So we're going to say 10.0.0.5. What this means is if you see a packet that is destined to any IP address in this subnet as its destination address, you're going to forward it to the next hop, 10.0.0.5. That's the only thing we're going to know once we put that in. So I'm going to also put one in for the 10.0.0.8 network. So we're going to say for 10.0.0.8, we're going to forward to the 10.0.0.1 next hop. So you want the network ID in there and the mask. Okay. So now if we show IP route, now we have two static routes. That's what the S means for the 10.0.0.8 and the 10.0.0.12. And the thing after the via is the next hop address, and that means send this out. And then we have the hop count and the administrative distance. So the first one is the hop count. So we're one hop away. The administrative distance is very trusted. This is the believability of the route, essentially, in iOS specifically. But we trust it because we put it in there manually. So we're going to go ahead and save that. And if we try to ping that same address, 10.0.0.0.14, it's still going to time out. And the reason is because the remote side doesn't have a route back to the networks connected to us. So from here, let's go down to this other router here. And we're going to put in those routes. So with the networks we want to reach are going to be 10.0.0.4. And our next hop is 10.0.0.13. Again, that is a /30. And then we also want to reach the 10.0.0.0, and that is the next hop of 10.0.0.9 /30. My goodness, today. All right, that's a /30, and then that's 10.0.0.9. All right, we're going to save that. We should have two routes. We do. All right, we should understand what those mean. And we're going to say exit there. And now the middle routers are connected to both of these networks already, all four of them. So we don't have to put static routes in there for these networks. Well, actually, that one is still indirectly connected. But at least for what we're doing, these two should be able to communicate at this point. Just for the sake of time, I'm going to go ahead and try to ping that. And there we go. Now, to fully complete this, though, what I would do is go on to router 2. And from the perspective of router 2, if I want to get to 10.0.0.4, I put the network ID in and the mask. And the next hop can go either way, but we're going to say 10.0.0.2. So then we should have a static route for that network. And if we want to reach the 12, 10.0.0.12, we can, in this case, go out 10.0.0.10. And then we should have a route for those two. All right, and then that connects it. That allows that router to route packets to those 4 and 12, those network IDs. And then for this router, if we want to put in the 0, 0 and the 0 network and the 8, we're going to put 10.0.0.0 with that mask. And I think you get the idea. It is quite tedious with static routing. That's what I'm trying to get across with this. So we got 10.0.0.14 will do for that one. And then let's make sure that it's in the routing table. It is. And one more. So the 10.0.0.8. And then that goes to the 10. Let's do 10.0.0.6. All right, so now we should be able to ping 10.0.0.1. All right. And packets going to the other side of that router, 10.0.0.9, so that's the 10.0.0.8 network /30. That'll go out the other hop. So some of them will go this way, the others will go that way. Now, this is static, though. And it's static because as the administrator, we have to put them in there, and we have to know not only which direction we want them to go, but what router knows how to get to that network. So it is a lot more overhead to maintain this over time. But this is good for smaller networks, maybe 4 routers, 5 routers, something smaller like that. But if you get above, like, let's say 6 and then 6 plus, I would really recommend dynamic routing. And that's what we're going to talk about in the next few labs, is that we're going to set up a few dynamic routing protocols, and you're going to see very quickly why dynamic routing has advantages over static routing. So I will see you in those labs, though. And again, this is how you set up static routing on a Cisco router. It's pretty much the same thing across every router vendor out there. It's the same concept. You're just programming in manually instructions to say, hey, how do I get to the 10.0.0.0 network? I send it out to 10.0.0.14. So that's all we're doing with static routing. I'll see you in the next one. All right, so now we're going to configure dynamic routing. So the difference is, now we're going to configure protocols that will automatically tell other routers what networks a certain router knows about. So all 4 of these routers are going to have a protocol that tells the other ones it's connected to what networks it knows about in its routing table. So if we go to the first one, if we do show IP route connected, what we're going to do is tell routing information protocol in this case, but any routing protocol operates like this. We're going to say 10.0.0.0, hey, I'm connected to that network, and 10.0.0.4, that network is connected to me as well. So to do this, we're going to do configure terminal and do router RIP. And this enables a routing protocol on Cisco IOS. And every router vendor has their own implementation of these protocols. But they all do the same thing. I don't care if it's Juniper, or Fortinet. They have some form of routing protocols like this. So the first thing we want to do is version 2, and this is because version 2 has improvements over version 1 of RIP. In version 2 we use multicast, whereas version 1 uses broadcast. Multicast only sends to the group that wants that information, so it's more efficient. So the next thing is no auto-summary. And essentially, this is a good example. These, the 10.0.0.0 and 10.0.0.4 networks, they could be combined into one subnet by changing the subnet mask and then sending the one subnet mask out as a summarized advertisement. In this case, we're saying don't do that. That's what no auto summary means. But from here, all we have to say is network, and this statement means any interfaces on this router that fall in any of the networks we're going to type here, that fall in this IP range, we're going to advertise. So we're going to say 10.0.0.0. And what this means is, because it's only going to look at the first octet of this class A address, that anything starting with 10 and anything else will be advertised. So we can say 10.0.0.0 and 10.0.0.4, but the other way would have picked them up as well. So we're going to go ahead and have that, and then we're going to save. And now we're going to do show IP protocols. And you can see that it is running, and it's picked up the Fast Ethernet 00 and the Serial 000 interface because they are both in the 10 network. All right, so now that that is accomplished, definitely make sure it's saved. And we're going to exit. And now he's sending out packets every few seconds out of these interfaces. So now we're going to do the same thing on R2, show IP route connected. We want to advertise with RIP. We want to use version 2. We want to say no auto summary. And we want to say network 10.0.0.0. And again, that would catch both, but we can also say network 10.0.0.8. Doesn't really hurt anything. And from there, show IP protocols. And then for that, we have 00 and, 01. And now the cool thing is, without having to type an IP route command like before, we will be able to see the 10.0.0.4 network as well. So if we do show IP route RIP, now we have the 10.0.0.4 network in there, and you can see the next hop was automatically put in there because it heard about it on the first router's interface going down. So RIP advertisements went down automatically. So that is how we configure that though on that router. And then we're just going to do the last two. And what will occur is the same thing. We'll have what's called convergence in the network. And what convergence means is that all the routers know about the state of the network essentially. So they know how to get to everyone else and everything like that. So 10.0.0.4, 10.0.0.12. Remember, show IP protocols is very important because it shows you any routing protocols that are configured. And it shows you like the effect of no auto summary and all of that. And then those interfaces are in there. And we should be seeing RIP routes for the other two networks, and we are. Good. Now we're going to go down to that last one. And we're going to do this same process. show IP route connected. And then we're going to do router RIP version 2. No auto summary, and then say network 10.0.0.0.8 and 10.0.0.12. And save that, and then do show IP protocols. And then there we go. And then if we do show IP route RIP, we have 2 indirectly connected routes. Now with RIP, the admin distance changes to 120 by default, and the hop count is 1 hop away. What this means is static routes that we configure directly are more trusted than a routing protocol by default, because routing protocols can fail. So what you need to realize is if a routing protocol fails, the RIP routes for those remote IP networks are going to get deleted and flushed. So when that happens, then the router doesn't know how to route to that network. So traffic flows can stop because of that. So you can also make things like floating stack routes where you set the admin distance higher than the routing protocol. So it uses the routing protocol normally, but if the routing protocol fails, the next best route, which is would be our static floating route, will actually get injected in the routing table and be used instead. So, like for instance, if I want to do real quick IP route to the 10.0.0.0.0 and say 10.0.0.9, I'm sorry, the /30 to the 10.0.0.9, and then say 150. And now, if I do show IP route, we still have a route there for RIP, but now if I say no router RIP, save that. Then if I do show IP route, look at that, I have that floating static route that came in there with an admin distance of 150. So that's one thing you want to think about with routing protocols. But that is how you configure RIP and why it's important. So in the next few, we're just going to configure a few routing protocols that are important to know. Alright, so now we're going to talk about EIGRP. So this is a dynamic routing protocol as well, and it's similar to RIP, but there's features in it that give it advantages over just using RIP, and of course over using static routing. So we're going to go into here. We have the same IP addresses and the same routers, but in order to set up RIP, we're going to do show IP route connected, and we want to advertise those 2 networks. Now in order to set up EIGRP, so with EIGRP we want to do router EIGRP, but at the end of this we want to put a number, and this is an autonomous system number. Excuse me. And this is it's basically a group of routers that all have the same routing table contents. So they're under one administrative control, basically. So let's make it 100 right now. And after this, we're going to say no auto summary for the same reason. We don't want this to summarize those 2 subnets together. Now, we actually need to be more specific with our network statements. We're going to say network 10.0.0.0, and then we're going to use a wildcard mask, which is the inverse of a subnet mask. So where there would be 255s in the mask, we're going to put zeros, and where it would be 252, we're going to use the last 3 bits available there, and then we're going to do 3. Okay? And this specifically says the 10.0.0.0/30 subnet. So we're being very specific. Only the interface that has that subnet assigned to it will have EIGRP packets advertised out of it. So we're going to enter on that, and then we also want to put in the 10.0.0.4 10.0.10/30 network like this. So now if we go back and do show IP protocols, we are now having EIGRP 100, and we're routing for the very specific 10.0.0.0/30 and the 10.0.0.4/30. So now there's important things about EIGRP versus RIP. We don't just advertise the update packets out of our interfaces that are participating in RIP. In EIGRP, instead, we have to make a neighborship first. So we have to basically agree with our neighbor on certain parameters before we're able to tell each other the networks we're connected to. So some of the parameters that are important are the autonomous system, the K values, which are values used to calculate the how preferred a route is. Okay, well, those are what the K values are. And bandwidth and delay are your basic K values that are used. But there are others. There's, load, MTU is one that's used, and other things like that. Now, it depends on who you talk to if MTU is used or not. There are, if you just Google EIGRP K values, you'll see a huge list of them. It does not matter for this, because we're not going to change them. That's why it doesn't matter. We're going to use the defaults. But anyway, the autonomous system, the K values, and if you are using a password, you want that to match as well. So we're going to go down here to the second router and show IP route connected. And then what we're going to do here is go into configure terminal, router EIGRP. We want that autonomous system to match. It has to match. Then we're going to say network 10.0.0.8. All right. And then network 10.0.0.0. Okay, and we see a message. Neighbor is up, and the specific interface is fast Ethernet 00, and the neighbor is 10.0.0.2. So what this means is, if we do show IP EIGRP neighbors, we have 10.0.0.2, and he's been up for 16 seconds. So what happened is we agreed on those values, and we decided to exchange our routing table information. So if we do show IP EIGRP topology, this is that routing information. Now, we have a connected one, and we have this other one here, and the connected interface. The feasible distance is very important to understand because it's a combination of what the neighbor router is reporting and our distance to that neighbor's network it's reporting. We add both of those together, and then we get the feasible distance. And what happens is the feasible distance is used to decide if that route should go in the routing table. Okay? Now, we actually have to calculate these, and when it's been properly calculated, you'll see passive there, and that's what you want to see. If you see active, that means it hasn't calculated the best route for that network yet. But these have, so if we do show IP route, we're going to see a D here, and that's for the dual algorithm, the diffused update algorithm, and that's for the 10.0.0.4. You can see the administrative distance here is 90 of EIGRP, and lower is preferred. So that means EIGRP routes and RIP running on the same router. RIP routes would not be put in the routing table where EIGRP routes would. So when you start using them together, only some of them may make it into the routing table. But that's also there, the feasible distance, okay? And then the next hop. So, same thing, we can check our protocols to make sure everything's right, and it is. And then, now that we got the idea of how it works, we're going to do the same thing on this router here. show IP route connected, and then router EIGRP 100, no auto summary, and I forgot to do it on the other router, so we're going to go back there, and 10.0.0.4, and network 10.0.0.12. Alright, and then save that, and let's go back and add no auto summary over here. And, okay, and no auto summary. You'll see that it does have to resync when you change a parameter, but it's okay. Now we're going to add the last config down here. And router EIGRP 100. And we want to advertise the run EIGRP on the interfaces that fall in this subnet. And this subnet. All right. Never hurts to make sure that you ran the command correctly. All right. So now if we do show IP route EIGRP, we have access to the remote networks that we didn't before, and we should be able to ping. Whoops. A few too many zeros there. We can ping those networks. And we can also ping the network, let's see, 5 and 6. And we can ping those as well. So we're all good there. Let's go back up to these here. And that means we should be able to ping the 10.0.0.9, 9 and 10. And we can also ping 13 and 14. All from those EIGRP routes. So remember, you need EIGRP to have a neighbor before the topology table can get routes, and then the topology table calculates the shortest route, like here, how there's 2 routes. It could load balance over that if we change the variance, where we can include both of those in the calculation, but we didn't in this case. And this one here is going to calculate the best route based on the feasible successor, the feasible distance, and then the successor route goes in the routing table, and then the feasible successor can be the backup route, and that takes over if one of them goes down. So then we go show IP route, we can see from that topology table only the 10.0.0.8, 10.0.0.12, the route to 10.0.0.1 made it into the table. 10.0.0.5 here is the feasible successor. So that's how the neighbor table and the topology table work in EIGRP. Alright, now we're going to talk about OSPF. This is open shortest path first. Now this uses the Dijkstra algorithm, and we're going to see that it's actually pretty scalable once we get into the configuration. So let's go ahead. And let's see here. These pretty much are the same config. It's a little bit different with OSPF. So what we do is router OSPF and then a process ID. Now, this is only locally significant, so they don't have to match. This is not an autonomous system number. But from there, though, we don't even have to do no auto summary, because this is actually accepts advertising the whole subnet and everything. So we're going to do network, essentially just like EIGRP. We're going to do 10.0.0.0 with the 0.0.3. But this time we're going to put it in an area, and we need to have at least the area 0. And area 0 is the backbone area in OSPF. And this area essentially is the main database in OSPF, and then there's other areas that are separate databases, but it's just a logical separation of networks because each area runs the Dijkstra algorithm independently. So the bigger the area, the more stress on an individual router because there's more networks that it has to go out and calculate the shortest path for. Okay, so this network is just going to be inside of area 0, and then we're going to do 10.0.0.4, and this one is going to be inside of area 0. All right, that's all we're going to do for this router. It looks pretty much the same as the others so far. And same thing, we're only advertising those 2/30 networks. Okay, we're going to save that and exit. And this is very similar. You need the same area, the same hello and dead timers, and the same password if you are using authentication. Remember, they're not going to just share information. So we're going to go router OSPF 1. You don't have to use the same process ID. 10.0.0.0. And then when we do area 0, we're going to see it come up. The neighborship, because they're going to be on the same network there. And again, it does take a second. And there we go. So now we should already have an OSPF route for the 10.0.0.4. And you see how the amend distance is 110, and then the bandwidth for that route is 65. And we're going to go ahead and have this router next. Do show IP route connected. And then we're going to do router OSPF 1, network 10.0.0.4, 0.0.0.3. And then we're going to have this one be area 0. And network 10.0.0.12. Alright. Then if we do show IP OSPF neighbors, we're in full state and we're fully, we have everything for that neighbor, all of its information. So if we do show IP OSPF database, we have the link state information for every network here, and we're calculating everything based on that. So these two other networks. So we're going to go ahead, put it in the last router here. And router OSPF 1 network 10.0.0.8 0.0.0.3 area. You know what, actually, let's see, the 8, I'll show you this as well. We're going to put this network, well, actually, you know what, that'll be a separate video. Area 0 for it, and then 10.0.0.12 0.0.0.3 and area 0. We should be good with show IP route. And now we should be able to ping 0.0.1, 0.0.2, as well as 5 and 6 by using our OSPF routes. And again, remember, you have to have the neighborship, all right? And the designated routers, because we are on an Ethernet network, it has the designated router and the backup designated router election. Now, we're also going to explore multiple area OSPF. This is simply when one interface is in one area and then one is in another. That's where you have an ABR router, an area border router. One interface is in area 0, let's say, and it has to be in the backbone area. And the other, let's say, is in area 10. We're going to explore that as well. All right, now we're going to add on to that OSPF configuration and do multiple area OSPF. It's basically we're going to take the groups of networks that we're doing calculations on, and we're putting them in two separate databases, one for area 0, one for, in my case, area 10. And this is how you scale OSPF. So we're going to start up here because I've only undone the config on 2 routers. We're going to do show IP route, and what we're going to do is router OSPF 1, and the network statements are where you make the distinction. So we're going to do 10.0.0.4 and that /30. This one is in area 0, but we're also then going to do 10.0.0.0, and then this one is in area 10. Okay? So we have now interfaces that are in this subnet are in area 0 on this router. Interfaces in this subnet are going to advertise in area 10. Okay? So we're going to exit from there. So we already have the neighbor for 13, and that is in area 0, okay? And then if we go here, we're going to go ahead and then we're going to look at, first of all, the router OSPF 1, and then we're going to do network 10.0.0.8. That one is still going to be in area 0. And ABR at least needs one of its interfaces in area 0. And then that'll make the, neighborship there come up. Network 10.0.0.0. And apologies about that. So you see though, he's in area 0. And then we're going to do 10.0.0.0. But area 10. And if the areas match between the other routers, we will see a full loading done up there as well for another neighbor. And what that is a neighbor coming up for 10.0.0.14 and 10.0.0.6. But if we do show IP OSPF database, we have one for area 0, and on this specific, what's now called an ABR, an area border router, in OSPF specifically, this now has another database for area 10. Okay? All this is doing is separating out the networks in the calculation. So if we had 100 networks, we could put 50 of them in area 0 and then put the other 50 of them in area 10, and then either one of those areas would only have to calculate routes to 50 networks as opposed to 100. So you could see, if you had 1,000, you put, 500 in area 0, 500 in area 10, that breaks it up and makes it more scalable for the Dijkstra calculation. But OSPF is one of the fastest protocols as well for calculating and reconverging if a route fails. But with that, though, that's a single area OSPF and multiple area OSPF configuration. Remember, you need to have that area match, you need to have a low and deads match, and you need to have that password match, as well as the subnet mask. It has to match as well. Alright, now we're on to BGP. So this is Border Gateway Protocol. Now there's two versions. There's IGP and eBGP. We're going to talk about both of those. And basically the main purpose of BGP is, instead of exchanging routes inside of one autonomous system like RIP, OSPF, and EIGRP did, we're going to focus on the external version where we're exchanging routes between autonomous systems. This could be enterprises, this could be between service providers, and things like that. And it's also used for, multiple WAN connections and everything is failover. Now, what we're going to do is simply configure a connection between AS100 and AS200, and using BGP, we're going to advertise this loopback network we configured. So let's start on the first router. And this is a path vector protocol. By the way, it's different. OSPF is a link state, whereas RIP was a distance vector, and EIGRP is an advanced distance vector, basically. A path vector is different than those. It uses different values to calculate the best route and things like that. But what we have here is our fast Ethernet 0, and then we have our loopback 1. And what we're going to do is do router BGP, and then we're going to give an autonomous system number. We're going to give 100, and let's double check that, yes. And we want to set up the networks to advertise. That's 10.0.0.0. And actually, you know what? Do show int f00 because I forgot the mask I had. 24 this time. So network 10.0.0.0 with the mask of a /24. And then also the loopback, the 2.2.2.0 network with the mask, again of a /24. Excuse me. Now, very important with BGP that's different, it doesn't dynamically discover other routers to exchange information with. You have to put in neighbor statements instead. So we're going to put in neighbor and the IP address of our neighbor. All right, so in this case, it's 10.0.0.2. Let's see there. Yes, it's 10.0.0.2. So 10.0.0.2. And then we want to put in remote-AS. And this is what differentiates external BGP from internal BGP, because if this number for this peer is different than our own autonomous system, it's external BGP. If it's the same, it is internal BGP. So this is going to be 200, and then we're going to go ahead and enter that in. So let's save that config and then do show IP protocols. Then we can see BGP is for autonomous system 100, and this is our neighbor. The neighbor isn't actually up yet though. So show IP BGP neighbors, we don't actually have any neighbors yet. So we're going to go ahead and go over to the other neighbor. So let's go over here. And this time we're going to configure the opposites. So we have router BGP 200 in this case. Remember, we have to specify those networks. So our networks here, and then we have to specify 1110. And this is a subnet mask, not a wildcard mask. Oops, don't forget to put mask in there. Okay, now we're going to specify neighbor because you have to do that too. And we're going to say 10.0.0.1 with a remote AS of 100. Now the neighbor is up, and if we do show IP protocols, the BGP autonomous system is 200 in our case, and this is our neighbor, and everything like that. So if we do show IP BGP summary, we have a neighbor, it's version 4, and we've received and sent messages in this connection. It's been up for 19 seconds. And there we go. So now, if we do show IP route BGP, we have one route because we advertised this route from our loopback. And that was indirectly connected, but it's also coming from an entirely different autonomous system. So this could be like two ISPs exchanging customer routes, or a transit route, or even with big enough enterprises, you may want to have them, merge, and those two autonomous systems would have to come together like this. But these are some reasons for it. But the concept at its core is still IP routing. It's just the fact that these scale to a lot bigger networks than, like, say RIP did. So we got 222, and we can ping that loopback. All right, there we go. All right, so now we're on to iBGP, and this is internal BGP. So the routes this will advertise are inside of the same autonomous system. So where this is helpful is actually, let's go back, like if we had two ISPs, and they're using eBGP, and they're exchanging, routes between each other. But let's say you have another connection, or, in between something else. But you don't want to overcomplicate things if you can help it, of course, by not having to run like OSPF, and then once you receive the BGP routes, the routes over eBGP, you may not want to redistribute them into OSPF, to put them in another part of your autonomous system in another router you have, or group of routers. Well, you can use iBGP, and you can have them be able to, you can have one router inside that's only running iBGP, and then give the routes received from the external router. From the external router, you can give them to the internal router and not have to run like OSPF and redistribute them. It makes things simple. Simpler than what it would be without this. So the difference is we're inside of one autonomous system. You could pretend we have autonomous system 200 over here advertising into this router, and then we're going to basically advertise the route from there into our autonomous system further. So we have the same IP address setup. So let's see. It's the same setup. So we're going to go to router BGP 100. But let's pretend we have the 10.0.0.0 with the mask /24. And that network 2222, the 2220 rather, with that /24 mask is what we have externally, and we're going to advertise that to our neighbor of 10.0.0.2 with remote IS 100. Okay, well, basically, this would be the same autonomous system. My apologies about that, but hopefully they'll add it in a future version. All right, well, basically, we would have said this is autonomous system 100 for both of these, and that 222 route, just like when we had BGP externally, would be able to go in and be injected. Basically, it would just be shared across, just like how we were able to then ping the 222 loopback after we set up a neighborship with BGP. But that's the basics of BGP, and really the difference between them is just the fact you're not sending them across autonomous systems. They're ending up in a routing table, that's inside of a router in the same system you're in. So they're not crossing autonomous systems with iBGP, but with eBGP they are. All right, now we're going to talk about HSRP and VRRP. We're going to start with the HSRP, but what they both do is just provide a failover for when one of the routers fails. It'll still will allow traffic to flow through the other router. So to do this, we have an active router that is in that role and a standby that is, standing by waiting for the active to fail. Now, these routers and their interfaces have normal IPs, so these are the management IPs. We have .2 here and .3 on the standby. And those are part of the 192.168.10/24 network. Now, the IP here, which is called the VIP, or the virtual IP, is .1. And this IP doesn't actually exist on the interfaces. It can move between the group of routers as they are participating in either HSRP or VRRP, depending on if the advertisements are being heard by the group appropriately. So For instance, if the standby doesn't hear advertisements from the active, the standby will take over the active role. So what we actually do is configure our client with the virtual IP of 192.168.1.1 there, right up here. And what we want to do is ping the server at 2222, and we want to be able to take out this interface here and still be able to ping. Now I've already set up OSPF between these three routers to exchange these networks and everything. We've already talked about OSPF. But now we're going to go onto this first router and then show IP interface brief. I'm going to put that IP on F00. That's 192.168.1.2 with its mask. And we're going to bring it up. And then for the HSRP configuration in the interface configuration mode, we're going to do standby, a group number. We're going to say 10, but they do have to match between the routers. And we're going to say IP, and then this is where that VIP goes. So 192.168.1.1. And we're also going to say preempt, which means if a router comes up that has a lower, better priority than this one, this router will still preempt it if it is the best router in the network, that is. So we're going to enable that as well as priority 255 because that's the best priority we can have. We want this router to be the active router, as you can see. We're going to save that config, and if we do show standby, we can see the state for this one is active. The virtual IP is 192.168.1.1, and the preemption is enabled. Now the standby router isn't known because we haven't configured the standby in that same HSRP group. So let's go over to that router. Same thing, we're going to go ahead and configure that interface with management IP. All right, bring it up, and we're going to say standby 10 IP 192.168.1.1. Again, that's the virtual IP. And we're going to leave everything else as it is. Save that config. And we're in listen mode because remember it's connected to a switch. So we have to finish the STP before we can send frames through the switch. Okay, now we're in standby, and that's what we expect. So now that this one's in standby, he's just going to listen for advertisements from the active one. But if they cease for any reason, he's going to go ahead and assume the active role. All right, so let's go down over here. We'll come back over to the client. And we're going to go ping-t 2.2.2.2. And if the OSPF and everything has the routes in the routing table, we should be able to go through and route to that machine. You can see they're going up to the left there because the active router is managing the traffic. And if we do a trace route, trace cert rather, to that server IP, we're going to 12 to the next hop of 10.0.0.1, and then on to the server. So if we do that ping again continuously, let's go into the active router. And all I want to do is go to fast Ethernet 00. I want to shut this interface off. You can see the OSPF neighborship went down and everything. But you will see the request timeout. And they should still continue through the standby router because he's the only router that is up to basically accept that traffic. And there we go. If we look in the console of the standby, you see an HSRP state change message on that interface, group 10, state, standby to active. That's what you want to see. All right, so now if we do a trace route, you see we didn't get interrupted whatsoever. Now we're going to 1.3. And if we bring this interface back up, the preemption should allow it to take back over, which is what we want to happen in this case. Of course, the STP has to, finish its calculation. So we'll give that 1 second. And there we go. So now we're active again. And if we go back over here to the PC, we should still be able to ping 2222 through that router. And there we go. Now you notice we're going through 1.2 again. But we can still reach the router. So that is our HSRP configuration. All right, now we're going to talk about our WANs, or wide area networks. So I'm just going to talk about some common ones. Some you'll see, in homes, some in businesses. And, both of these can be used in either, all three of these. But we have a leased line, and that's a T1. And with a T1, we use a serial cable. And one end provides clocking called the DCE side. And then the other side provides a termination point called the DTE side of it, so the client equipment. So this is like the CPE, the customer premise equipment. All of these here, the CPE. And for this here, with this type of equipment, let's essentially set up a host name real quick, and then we're going to go to that first serial port. We'll set a clock rate, 64,000, and we're going to say IP address, let's say 10.0.0.1, all right, with the /30. Save that configuration. And then we're going to go here to the CLI. R2. And then we'll go to that serial interface and say IP address 10.0.0.2 on the network. Now remember, because this is our WAN, we would be saying IPNAT outside like we did before, and then if Fast Ethernet 00 was the inside, this would be IPNAT inside. And then you remember the last thing we do, you'd want to set up that, so we would set up the address here, our private, then we would set up our access list, and then we would permit that traffic through to be natted. And then what was the last thing? You remember you got to put it together with IPNAT source list 1, and then interface would be the WAN interface, serial 000, and we want to overload. So that's how we configure that type of WAN. You can also secure this by setting up PPP, and with that you would set a username to the to be the one configured on the far end, like R1 in this case, and set the password, to whatever you want. And then you'd go into that interface, and then on both sides, if you want two-way, you'd configure PPP authentication CHAP, and then you can also fall back to PAP, and that would authenticate the link before you can send packets across it. So that's a type of way, that's a way to secure a leased line. But that was also how you use NAT with that as well, how you can combine the two together. So let's go over to the next one here. And with the next one, with the DSL modem, we would just use our Ethernet interface and plug it right into the modem. And then that would go on a coax line out to the ISP. And then basically we would do very much the same thing. We would go into one of our interfaces, set that to be a private address, like 1.1, IPNAT inside, and then we would go into F01 as our WAN, set the IP there, whatever it may be. You know, in this case with a DSL modem, it may be DHCP, that's fine too. And then we do IPNAT outside, and then just IP access list, standard 1, permit our LAN addresses to be natted, and then you want to combine them. Always combine them together, because otherwise it's not going to work correctly. Alright, just like that. So that's how you'd set up a cable, a DSL connection. And lastly, with the cable connection, very much the same. You pretty much already know the configuration. We're going to go here, we're going to plug it in, set up our host name, set up one of those interfaces to be the WAN and everything, and then all of that. And we're going to say IPNet inside. And remember on all these interfaces to do no shutdown and everything. And that was 00, so we're going to do 0, 1. This could be DHCP. We could also pretend it's static. That's fine too. But the main idea I want to drive home is NAT is very important for every WAN configuration. You're going to want NAT because, remember, you have to have those be able to route out to the ISP so they're not blocked. And then we'll just say IPNAT inside, source list 1, interface. But the idea is, regardless of what whatever the modem is, your configuration on the router is still the same. Okay? That's what I want you to get from the video. Is it's not really that much different. It's the same configurations and the concepts. They just can carry over to different WAN connections. The idea of a wide area network is it just connects our router to somewhere else. And as we said, always make sure to bring that interface up, because that's going to save you some trouble with your WAN connection. If your WAN interface is down, you're not going to get very far. But that is the three main types of our WAN connections. And actually this one, I think I did forget to bring it up as well. And there we go. And then from there we can ping It does take a second to come up, but then we can ping across the link to get to the other side. And these I don't have an IP address, but this would go to your provider's head end here, and then this one would as well. This one can even be a point-to-point connection, actually between only like your building in, point A and then another building in point B. Well, that can be all the WAN connects. It can go through all kinds of property to get there, but with the other two WANs, or a satellite or fiber modem I want to add as well, those go into a head end that all the customers' traffic goes into. A leased line is more expensive because it is physically private. You don't logically share it with any customers like you do on a cable or DSL or satellite or fiber modem. You're sharing that with a bunch of other customers. So that's also why encryption is very important, things of that nature. But that is how we set up some basic WAN types and what you may run into.